All right, so today we're going to get into ionic compounds. So ionic compounds are compounds that are made of charged elements. So remember, ions are atoms that have lost or gained electrons, and they'll tend to lose or gain electrons to be like their nearest noble gas. So important things to remember, cations are positively charged ions, right? So some key things here, they're cations are positively charged, and they're formed from metals, right? So if we look at our periodic table, right, we have our group 1A, 2A, 3A, and then we have our stairs, right, that kind of go down here, right? And then we have 4A, but only the metals down there, right? So only metals. And then we have some special metals here. And then all of these metals. So these form variable positive charges or transition metals, right? So our anions then, our anions are going to be negatively charged, and they're going to be formed from nonmetals, right? So my nonmetals here, right, will be 5A, 6A, and 7A, right? So those will be my nonmetals. And you'll notice that the charge on the noble gases in the last is 0, right? So our representative metals, our representative elements, will be all those that form common charges, right? When we start talking about ionic compounds, it's important to know that they'll all have a net charge of 0, and I'll get to that. But remember that all the things to the left of the stairs will form positive cations, and the things to the right of the stairs will form negative anions. All right, so you should have already gone through a slide presentation that talked about Lewis dot diagrams. I do mine just a little bit different than it said. For instance, if we took calcium, right? We took calcium. So the Lewis dot diagrams, I kind of picture a box around it, not a plus sign. Right? And each side of the box represents one of the bonding orbitals, or the valence orbitals. So valence electrons are those electrons in the s and p orbitals. So there's one s and there's 3 p's. So together that makes 4. So if you think about it like this, we have s, we have the px, the py, and the pz. So those are our 4 valence orbitals. So calcium is in 2A. So calcium has 2 electrons, right? Now these electrons will occupy orbitals. So but remember, I can only have maximum of 2 electrons in any orbital system. And then Hun says, right, they have to be as far apart as possible. So I'm going to put them as far apart as possible, put them like that. Right, so if I was going to do the valence orbitals, I'll give you one other example. If I was going to pick chlorine, right, chlorine's in 7A, right? Now let me give you a different scenario. Let me give you oxygen. So oxygen is in 6A, right? So I'll have to put 6 valence electrons on it. I'll go one at a time. I'll go 1, 2, 3, 4, 5, and then I'll want to make these last 2 as far away from each other as possible. Now, the way that ions become, or atoms become stable, is to be like the nearest noble gas. It's going to be called the octet rule we're going to talk about. And the only way that's going to happen for calcium, if it can get rid of these 2, and for oxygen, if it could fill all 4 orbitals, right? So this will actually transfer electrons that way. So the result of that is going to be a bond of calcium and oxygen. Now the calcium will have a 2 positive charge because now it has 2 less electrons than it does protons, and oxygen is going to have a 2 negative charge. All right, so when we talked about the resulting charge, when these come together, the result's going to be 0, right? Because they're going to equal each other out. All right, we'll talk about that in just a second. All right, so that's our valence orbitals, right? We can see our oxygen that we just did right here. All right, we can see our calcium we did there. Now, I don't like the way they did calcium because those would not be bonded, right? So Hun says I can't pair those up until I've left them unpaired within their valence orbital. All right, so the octet rule, right, that we just talked about. So the octet rule says, right here, atoms will gain or lose electrons to fill their valence orbitals. Right? So the metals will lose to be like the previous noble gas, and the non-metals will gain to be like the next noble gas. Right? Right. So, so if we look at our valence electrons, we'll have our common ions. So in group 1A, right? In group, oops, I don't want to do that. So in group 1A, they'll form a 1 positive charge. In 2A, they'll form a 2 positive charge. If I skip all the transition metals, 3A will be 3 positive. In 4, I'll get my 4 positive charges, right, for my non-metals, or for my metals. But some of those can form multiple charges because they're more like transition metals. When I get to 5, right, so these ones in 1A, they want to be like their previous noble gas, so that's why they have to lose. But when I get to the non-metals, like nitrogen here, right, so the transition to 3 negative, because it has to gain 3 to be like neon. Right, so 6A will be 2 negative because oxygen will have to gain 2 to be like neon. And the halogens, right, will be 1 negative because they'll have to gain 1 to be like their nearest noble gas. And then the noble gases are already full, so they're not going to gain or lose anything. Right, so that's the way we kind of look at that. So properties, the reason why they form ions is because they're more stable, right? And all these properties exhibit being more stable. You saw in that last video is if you throw anything in that 1A group, those alkali metals, into water, they're so reactive they'll just start flipping electrons all over the place. And they showed you they dropped cesium in there and it blew up the cup. But when they lose that electron, they become stable. Right? Sodium is highly reactive. Right? Sodium will cause lots of sparks to fly from water. But once it forms an ion, right, it's completely stable. It's in salt. Right? We can heat it. It's actually kind of good in small amounts for us because it helps us conduct electricity in our body. Right? So here's the important thing here. Most dissolve to form an electrolyte solution. We're going to talk about electrolyte solutions a lot later. Right? That's a solution that's a good conductor of electricity. Right? So make sure you know that. Right? So if I had a salt, a block of salt, it wouldn't conduct electricity, but if I dropped it in water, it would do a really great job. And the reason is, if I have sodium chloride, right, and I'll put an S for solid here, the charge on it's 0. But if I drop it in a beaker of water, it'll dissolve into its ions, right? They will be no longer attached. Now I have charge. Right, so if I stuck pieces of metal in here, right, and I connected them with a wire, right, one of those metals would have a positive and a negative charge, right, and the electrons flowing from the negative to the positive would latch onto a sodium that would carry that charge over. So that's what an electrolyte is. So it's a solution with charged compounds that can conduct electricity. All right, so type of ions. Right, so we have monatomic, mono meaning 1, made of a single atom. Right, so monatomic ions are those things from the front of the periodic table. Right? And then we have polyatomic ions. Poly means more than one. Right? So polyatomic ions are covalently, right? They've learned in biology probably. Covalent means they're sharing electrons, so we'll talk about that next chapter. Right? But they have unequal amounts of electrons. So polyatomic ions are groups of atoms with a charge. Right? No matter which one, they'll be pretty easy to do, and we'll give you lots of help with that. So monatomic ions. So the rules for monatomic ions, they form for metals, right? We already talked about that. We have our simple metals. I give you an example here, right? So they form cations, and they retain their name. So lithium ion is still called lithium, right? And beryllium ion is still called beryllium, and iron ion is called iron. But once you get to these transition metals here, there's different rules, right? So some transition metals form more than one. So for this, if you looked at iron, I would have to say iron 2 or iron 3. So this is what we call the charge number. So iron 2 means it forms an iron with a 2 positive charge. Iron 3 forms iron with a 3 positive charge. So I would have to tell you if it's iron 2 or iron 3, so you would have to know the charge. Right? If it's in a compound, I'll show you how to figure out the charge from that. Right? So some transition metals, like I said. So those are how we do metals. Right? And the other ones, they form charges based on the group. So 1A forms a 1 positive charge, 2A a 2 positive. And aluminum by itself here in 3A forms a 3 positive. Almost everything else, right? So all this right here, right, are simply transition metals, right? And they form multiple charges. There are 3 exceptions, right, to that rule. Right, so this, zinc, cadmium, and silver. So make sure you write this down somewhere. Zinc, only form a single charge. So what that means is no charge number. So when you list those, it'll just be called zinc, it won't be called zinc 2. It'll be called cadmium, not cadmium 2. So those are your exceptions to that rule right there. Right, so we have polyatomic ions. Now I've given you a polyatomic ion list. I used to make people memorize this, but I can't make you memorize it because you're at home right now. So look at the polyatomic ion list. But the polyatomic ion lists, they have standard charges associated with them. And when I move them, when they make compounds, they stay together as a unit. Right? And we'll talk about that in a little bit. So binary compounds, right? So a binary compound has 2 types of ions in it. That's what binary means. Bi means 2. Right? So it has 2 types of compounds. For instance, lithium and oxygen, right, come together, and they form lithium oxide. Right? So the naming is the anion gets the suffix IDE. Calcium and chlorine come together to make calcium oxide. Right? And I'm going to show you how to make these compounds. So the important thing is when I put them together, the compound has to be neutral, right? And that it has to be reduced with its subscripts. The subscript is this one at the bottom right there. Right? So it has to be neutral and it has to be reduced. The way we do this is we'll talk about what's called the crisscross method coming up. So if I'm going to make a compound out of these ions, right, since the oxide has a 2 negative charge and the lithium has a 1 positive charge, I would have to have 2 of these lithiums to cancel out the oxygen. Right, because now the subscript multiplies what's in front of it. I have 2 positive charges and 2 negative charges. So my overall charge would be 0. When you write the compound, it's important that you don't have charges anymore because they're neutral, right? They cancel each other out. If I looked at this next one here, Actually, I'll use green for this. So if I look at the next one here, right, same thing. Calcium has a 2 positive charge. Chloride has a 1 negative charge. Right? So I've got to take that 2, I've got to put it over here, and that's why I would get the calcium chloride. Again, this has a 0 charge to it. So the crisscross method is an easy way to do things. So the way the crisscross method works is you first have to write the ions with the charges, right? And then you'll bring the number, not the charge, the number down to the opposite ion. So if you look at this example here, right, the S has a 2 negative charge, the magnesium has a 2 positive charge. So essentially, I would bring 2's down to each one of them. Now, in the end, we have to reduce our formula, right? So that's our formula. I have a net 0 charge now. So we have to reduce the subscripts, right? So essentially, you're making whole numbers out of them. And we don't write ones, so I get magnesium sulfide. So that's my compound. If I looked at the next one, right, I would have to bring the 3 here, and we don't write ones. So now I have 3 positive charges and 3 negative charges, and that's why I get K3N, or potassium nitride. Right? The anions get the suffix I. Right? Same thing here. Right? So I would have to, if this is going to be my compound, I would have to bring the 2 down here, and I have to bring the 3 over here. So now I have 6 negative charges and 6 positive charges. Now we get aluminum oxide. Okay, so the crisscross works pretty easy. Now I'm only going to bring this up. We're not going to do examples of metallic bondings, but metals bond together to form alloys, right? So an alloy is a solution of metal. Right? So an alloy is a solution of metal. So metals are tightly packed, but they're all cations, right? So metals are made of tightly packed cations floating in what they call a sea of electrons. So if I have a bunch of copper, right? So we make wires out of copper. If I have a bunch of copper, copper is more stable if it doesn't have electrons in its valence shell, right? If it loses them. So if I have a copper wire, right, all these electrons it lost are floating in that wire. So they don't want to be attached to the copper, but they really have nowhere to go, so they're all sitting in the wire. So if I want to conduct electricity, right, and I want to push electrical current through there, the electron actually just goes in, and one of the electrons in the wire already leaves, right, because they're loosely attached. And that's the way it works. And that's why when you have static electricity and touch something metal, right, you'll get a jump of electricity. Right, so naming rules, right? Important to know how to name your monatomic ions, right? So the metal cation stays the same name, right? And the non-metal gets the suffix IDE, right? So if I have this, it would be sodium. Chloride. Right? If I had this, it would be so the chlorine becomes chloride and the oxygen becomes oxide. I could have strontium, nitride. Right, so polyatomic ions, right? So you keep the name of the polyatomic ion without changing the suffix, right? And they're oxyions or eights and ites, and you don't have to memorize that. Just know that you don't change the name, right? So if I have, for example, So if you look on your polyatomic ion sheet, you'll see that SO4 is sulfate. Right, so I would have sodium. You simply state the name of the polyatomic ion. Now the transition metals we talked about, right? You have to state the number of the charge after the metal. So here's where it becomes a little complicated. If I have something like this, then we have to start to look at, remember this is 0. If this was 3 negative, I have 6 negative charges. So this would have to be 2 positive to give me 6 positive charges. So you kind of have to work it backwards, crisscross. So now that I know that, I could call this copper 2, because that 2 is my charge number. If I had this, right, again, right, so my nitrate I know has a negative charge. So if I have 2 negative charges, this would have to be 2 positive to cancel it out. So this would be still copper 2. If I had something like that, same thing, right? I know that this is 0. I know that sulfate, if I look at my paper, is 2 negative. And so now I have 6 negative charges. I would have to have 6 positive charges, so that would have to be that. So this would be called iron 3 sulfate. Alright, so the naming game, you'll get good at it because you'll have plenty of help. Alright, that was kind of long, but good luck, and I will talk to you a little later.